It's time to experience something glorious. Unacademy Combat. Compete, crack, conquer.
A challenging gate contest engineered to give you an experience like none other.
Where you put your knowledge to test
and battle it out with a test
To bring out the best in you, Unacademy Combat is the most competitive, gamified contest for gate till date, with the best of the questions by best educators.
with detailed video solutions from top educators right after each contest.
Combat live with peers to get real-time rankings and win big.
Participate in every contest to improve your ratings.
Challenging contests every fortnight or alternate Sunday. Live ranking after every question. Big rewards for top rankers. Your passion to crack gate deserves this. Your hard work towards your dream deserves this. Fuel your inner fire for the ultimate gate challenge. Unacademy Combat. Register now.
A very good morning to all my dear friends. Welcome to Unacademy. कैसे हो मेरे प्यारे दोस्तों? I hope the audio and video are quite clear. So let's start the second last session, or we can say the third session, which is marathon session on strength of material. और इसको लीड कर रहा हूँ मैं, यानी कि आपका दोस्त ऐश्वर्य, जो गेट ESC के लिए आपको पढ़ाता है. And I have completed my masters from IIT Delhi and BTech from Jamia Millia Islamia. 4 times I have qualified gate with my best AIR 226 in 2011. I do have 7 years of teaching experience and 2 years of industrial experience, and I used to cover more than 50% of the subjects in civil engineering. Dear, this is our official Telegram channel. You guys can join this for the YouTube upcoming classes notification as well as the YouTube e-notes. And we do have many free content available on Unacademy special classes as well as on Unacademy YouTube channel, official YouTube channel. But still, we recommend our learners to go for our Plus and Iconic plan. The reason being, and in Plus series you are going to get classes on the daily basis. Weekly tests are there, structure courses are there, crash courses are there, rank improvement badges, and unlimited access to the content is also there. If I'm talking about the Iconic one, which is the superset of Plus, where you are going to get all the benefits of Plus. Apart from that, also you are going to get the personal coach who is going to plan your study, who's going to give the booster session for you, who's going to analyze your test at the personalized level. Not only this, also you are going to get the specialized notes and practice sets along with the dedicated doubt clearing educator. So whether it is a matter of Plus or Iconic, so feel free to use the code AISH10 Now, subscription prices. Okay, so Unacademy subscription prices are available from 3 months to 2 year in Plus. And if I'm talking about Iconic, then these models are available from 6 months to 2 year. So for instance, 10% of AISH 10 is key. In fact, not 10%. If you are planning your subscription today and tomorrow, then instead of 10%, you will be getting 20% till 31st Jan. सो कल रात 12 बजे तक अगर आप AISH 10 का यूज करते हो तो 10% की बजाय यू गाइस आर गोइंग टू गेट 20%. वेलकम डियर रवि. सो कॉम्बैट आपका अभी होने वाला है 11 बजे से है एंड इट इज द लार्जेस्ट वीकली कॉम्पिटिशन फॉर गेट. नहीं एनरोल किया तो कर लो, अभी तक कॉम्बैट नहीं दिया तो दे लो. एंड हियर यू विल बी एबल टू एक्सेस योर प्रिपरेशन इन लेस देन 60 minutes. So you are going to get 100 lucky participants are going to win exciting gift vouchers and gadgets like Samsung tab, JBL speakers, Amazon voucher, and you can also stand a chance to win up to 100% scholarship. And the scholarship pool is of 4 crore rupees and you can experience the thrill of live test. It is the best and effective preparation for GATE 2022. And not only this, the detailed video solutions are also provided by top educator and questions are also curated by the top educators. You can see new batches have been started in not only in civil but also in mechanical, electrical, EC, you can say mechanical, etc. Evolve batch or asset batch में dear we have started strength of material and again I am welcoming you all guys in the marathon session on strength of material. So already we have done up with the 2 sessions and the syllabus which we have covered so far is on your screen. Stress and strain we have covered yesterday, session 1. This also we have covered in session 1. This also we have covered in session number 1. इसलिए बता रहा हूँ ताकि जो लोग रिवीजन कर रहे होंगे उन्हें पता चल जाए कि कौन सा टॉपिक कौन से लिंक पे मिलेगा. SFD BMD ट्रांसफॉर्मेशन ऑफ स्ट्रेसेस, ये थोड़े से SFD BMD में हमारा टाइम ले लिया था, ये हम करेंगे सेशन 2 पे. ठीक है. नाउ दी simple bending, torsion, shear, at least these 3 topics I will be covering now. Combined stresses भी. और जो इवनिंग सेशन होगा, जो आफ्टरनून सेशन होगा, जो 2 बजे से होगा, उसमें आई एम प्लानिंग टू कवर दीज मैनी टॉपिक्स: प्रेशर वेसल, स्प्रिंग्स, shear center column and deflection of beam. So shear center column, springs, pressure vessel, all these are topics are small, not column but shear center, spring, pressure vessel, they are hardly 30 to 45 minutes topic and most of the time we are going to devote in session number 4, last session of Endgame Marathon, on column and deflection of beam. Okay, so let's start. I think no need of revision what we did yesterday. So last session was on SFD, BMD and transformation of stresses. We have seen how to draw SFD, we have seen how to draw BMD, how to draw axial force diagram. Also we have seen the significances of SFD, BMD as well as AFD. We have seen the common sign convention used in drawing SFD, BMD. After that we transfer our stresses to different planes and we have seen 2 approaches. One was analytical and another was graphical. The graphical approach was also known as Mohr circle. Okay, so let's start with the simple bending dear. Let's start with the simple bending equation. So do you know what is simple bending equation, all of you? Very commonly used, very important topic from strength of material and its application you can see not only in SOM but also in steel, RCC and up to some extent in structure as well. Okay, so simple bending equation, or in most of the books it is also written as pure bending equation. It is again given by Mohr. So anybody, what is simple bending equation? Yes, simple bending equation is simply m upon I is equal to sigma by y is equal to E by R. Now what is this m, what is this I, what is this sigma, what is this y, what is E, what is R? So we need to know. Okay, ये सब कुछ हमें पता करना है, but before proceeding further I would like to start with the assumptions which is evolved in this simple bending equation. Assumptions which are evolved in this simple bending equation. So shall we? So assumptions एक बार लिख देता हूँ, ये टॉर्जन के लिए भी काफी हद तक ये assumptions valid रहेंगे. So let me write down the assumptions for you guys. let me try in this way. Let's see whether it is working or not. So first assumption is plane section before bending will remain plane after bending. इसको तो मैं बोलता हूँ कि dear it is your BTech assumption. This assumption is your BTech assumption. Don't you think so? अरे एक मिनट. Yes. This is plane section before bending will remain plane after bending. Okay. So this is your assumption number 1. Second assumption is your material is homogeneous and isotropic. It is homogeneous and isotropic. Third assumption is that your material is going to obey Hooke's law. Third assumption is your material is going to use Hooke's law. Material obeys Hooke's law. Okay. Fourth assumption is that material is same in tension as well as in compression. Fourth assumption is material is same in tension as well as in compression, means its Young's modulus is going to be same in tension as well as compression. So we can say the modulus of elasticity, okay, so this is the fourth assumption. So what is the fifth assumption? That initially the beam is free from the initial stresses, or it is initially straight, and the dimension of the cross sections are not varying along the length of the beam. Okay, so dimensions of the cross sections are not varying along the length of the beam, and initially the beam is straight. So let me write it. And next assumption is that the plane of loading must contain the principal axis of cross section. This also is last assumption we can write. Next is last. Very good morning dear Manjeet, कैसे हो? Next assumption is that the plane of loading must contain a principal axis of cross section of beam, and load must be perpendicular to the longitudinal axis of the beam. Okay, so all these are the assumptions which we are drawing. Very good morning. Okay, so these are the assumptions which we are using before the derivation of simple bending equation. Although I am not going to derive the simple bending equation, okay, उसको derive नहीं करना हम लोगों को, but उसको understand करना है. We have to be familiar with all the terminologies. Okay. So once again I am repeating, the plane section before bending will remain plane after bending, and its meaning is simply that strain diagram is linear. Strain diagram is linear. Second assumption is my material is homogeneous and isotropic. It is homogeneous, it is uniform, okay, and it is going to show the similar property in all the directions. This is the meaning of homogeneous and isotropic. Third is that I can work linearly, means it is going to obey Hooke's law, means strain and stresses are directly proportional. Whatever you are getting strain, as from assumption number 1 you are saying that strain diagram is linear, it means from assumption number 3 which is saying it is obeying Hooke's law, you can also say if strain diagram is linear, then stress are also directly proportional to strain, means stress diagram are also going to be linear. So this is my third assumption. So third assumption indirectly says that stress diagram here is also linear. Stress diagram here is also linear. चौथा assumption बोल रहा है कि मटेरियल के साथ कोई भेदभाव नहीं है. ओके, यस. Good morning Aishu sir, my first Unacademy lecturer. Okay, great Ashraf Ali. Okay, Manjeet कह रहे हैं sir stress is strain upon area of cross section. Area of section नहीं, ये नहीं समझ में आया मंजीत, ये नहीं समझ में आया. But stress is proportional to linear, है ना. Okay, and material जैसा आपका compression में है, जैसा आपका कंप्रेशन में है, ठीक वैसा ही टेंशन में बिहेव करेगा. मींस योर मटेरियल, योर स्टील इज इक्वली गुड फॉर कंप्रेशन एंड टेंशन. ओके, सपोज द मैक्सिमम परमिसिबल लिमिट ऑफ माइल्ड स्टील इन कंप्रेशन इज 250, इट इज आल्सो yield value is also comes out to be same in tension. Okay, and fifth assumption is saying that your beam is going to have the constant cross section. इसका एक ही मतलब निकलता है कि आपके बीम का क्रॉस सेक्शन चेंज नहीं हो रहा. along the length as well moment of inertia is constant, area of beam is constant. इसको एक टेक्निकल टर्म बोलते हैं हम लोग इंजीनियरिंग में, that my beam is prismatic. प्रिज्मेटिक का मतलब होता है वो क्रॉस सेक्शन जिसके एरिया चेंज नहीं करते. ओके, और सिक्स assumption जो भी हमारा लोडिंग होने वाली है वो प्रिंसिपल एक्सिस ऑफ क्रॉस सेक्शन से होगी. मतलब अगर ये मेरे पास बीम है, ये मेरे पास बीम है, सो फॉर सिंपल बेंडिंग नो ट्विस्टिंग शुड बी इन्वॉल्व. अगर ये मेरा बीम है तो यहाँ पे जो आप बेंडिंग करोगे, यहाँ पे जो आप बेंडिंग करोगे, इट इज गोइंग टू बी लाइक दिस. इसका कोई ना कोई एक वो होगा सेंट्रॉइड, लोड इसके परपेंडिकुलर होगा और इसी एक्सिस पे आके लगेगा. मतलब ओनली बेंडिंग विल बी देयर, नॉट ट्विस्टिंग, नॉट ट्विस्टिंग डियर. ओके, नॉट ट्विस्टिंग. ओके, क्लियर है. सो ऑल दीज आर दी assumptions involved in the simple bending equation. Okay, so now by keeping these six assumptions in mind, we can derive the simple bending equation. Although once again I am repeating, yes, prismatic section means no changing of area. Manjeet, excellent. Yes. So but again I am saying I am not going to derive the simple bending equation here. This is the equation which we have to use, which we have to apply, on which we have to do our engineering. And believe me, once again I am saying this equation is literally very important. Now we need to understand what all are the various terms involved in this simple bending equation. Okay, so it's m upon I is equal to sigma by y is equal to E by R. Okay, so what all are the various terminologies? What is m, about which axis it is happening, what is moment of inertia, about which axis we need to calculate moment of inertia, where the stresses are being developed, what is y, from where we have to measure y, for which material we are talking about Young's modulus, for which direction we are seeking it, and what is this r, what is this radius of curvature, and what radius is actually coming into the picture. Okay, so we need to understand this simple bending equation. So let me explain these 6 parameter one by one to you. एक एक करके इन 6 को देखते हैं. But ये assumptions are very important. These assumptions are very important. Okay. Now let me again write down this simple bending equation here. Let me again write down this simple bending equation. So it is m upon I is equal to sigma by y is equal to E by R. इस इक्वेशन के सारे टर्म का अगर आपको विजुअलाइजेशन हो गया ना, तो सिंपल बेंडिंग इक्वेशन आप लोगों के लिए कुछ भी नहीं होती. ठीक है, तो हमें इसी को समझना है. तो पहले थोड़ा टाइम लूंगा इसको समझाने में मैं, क्योंकि मेन चैप्टर का रूट यही है. इसको पकड़ लिया तो चैप्टर के अंदर कुछ भी नहीं है, पूरा विजुअलाइजेशन आराम से हो जाता है. ठीक है, बेंडिंग मूवमेंट क्या होता है आपको पता है. ठीक है, मूवमेंट क्या होता है आपको पता है. सो लेट्स सी दीज टर्म्स वन बाय वन. For that, let me draw a 3D figure. Let's suppose यहां बनाता हूं नए पेज पे कि मेरे पास मान लीजिए ये कोई बीम है. Let's suppose I do have a beam here. Okay, ये मेरे पास कोई बीम है. Or let's say it is simply supported condition. Now all of you know what is a simply supported condition. Let me draw it over simply supported condition. Okay, let's say this is a support and this is also the support. Okay, and you have to apply load here vertical axis. You can apply load here in two ways. One like this, another like this. Both are going to work well. मतलब कि इसको मैं आपको कैसे समझाऊं कि अगर ये मेरा बीम है तो आप इसमें ऐसे भी लोडिंग लगा सकते हो, आप इसमें ऐसे भी लोडिंग लगा सकते हो. ओके, ऐसे भी लोडिंग लगा सकते हो और ऐसे भी लोडिंग लगा सकते हो. इट कैन बेंड लाइक दिस, है ना, ज्यादा नहीं करूंगा टूट जाएगा वरना. और इट कैन हैव इट कैन शो यू बेंडिंग लाइक दिस. ओके, सो इन बोथ द डायरेक्शन यू कैन शो द लोड, क्योंकि दोनों के कारण बेंडिंग हो रही है. बट यस, इफ यू आर गोइंग टू अप्लाई लोड लाइक दिस, so it is your torque. Due to that, twisting will happen, which is our next topic, and we do not have to consider that here. Okay, so for bending with respect to this beam, we would be having two possibilities. Okay, about this axis it is going to bend like this, about this axis it is going to bend like this. But if you are going to apply load like this, it is simply going to give you compression, and if it is passing through the CG, it is simply going to give you compression or tension. It is not going to participate in bending. Okay, so that is the case. So what can we do? Let me start with this vertical loading. Let me start with this vertical loading. So this loading must be passing through the center line, which contains the loading. It must passing the center line. Let me say like this. Okay, this is the center line. And why center line? Because if it is going to deviate from this center line, then along with the bending, it is also going to show you some twisting. For example, if I am going to take a load like this, if I am going to take the load like this, then due to this eccentricity, Due to this eccentricity, instead of bending, it is also going to give you some torque, some twisting moment is also there. Suppose this is P, then P into E is the twisting moment about this axis. So right now we do not want to tackle twisting problem. We only want to tackle bending problem. Okay, only simple bending is involved here. Okay. Okay. Or simply you can apply bending like this, or either you have to give this or you have to apply some bending, maybe like this, maybe like this. Okay, so due to these loads my dear friend, you can calculate bending moment at any section. You can calculate bending moment at any section. I hope you understand the dimension of this beam. This is the longitudinal axis and this is known as length, and this is the width of your cross section. This is the overall depth of your cross section, and let me make it this line hatched. The axis which I have shown with the blue, this is known as the neutral axis. You know why it is known as the neutral axis? Because all the rotation are going of the cross section are going to happen about this axis only. Let me call it axis, let's say ZZ axis. Let me call this axis as ZZ axis. Okay, and can anybody of you tell me, yes, applied load only surface to perpendicular? No, it is not necessarily perpendicular, it can also be inclined. It can be like this, Manjeet. Yes, ऐसा भी हो सकता है. But we have to make sure due to this load, it's plane containing in this red plane only. If it is deviating from this plane, then it is going to show you twisting. मीन्स आप इसको देखो, इसको ऐसे समझो. मैं आपको ये जैसे बीम बना के दिखा रहा हूं, लिसन टू मी. ये है, और मान लीजिए ये इसका सेंटर लाइन है, ये इसका सेंटर लाइन है. आप लोड ऐसे लगाओ, ऐसे लगाओ, ऐसे लगाओ, चलेगा, ठीक है, बिकॉज इट इज गोइंग टू कंटेन्ड इन दिस प्लेन ओनली. बट अगर आप लोड को ऐसे लगाओगे या लोड को ऐसे लगाओगे और उसकी निब यहीं पे रखोगे, तो उसके कारण क्या होगा? इट इज गोइंग टू गिव यू टू कंपोनेंट, वन वर्टिकल एंड वन हॉरिजॉन्टल. दिस हॉरिजॉन्टल इज गोइंग टू गिव यू ट्विस्टिंग, दिस हॉरिजॉन्टल इज गोइंग टू गिव यू ट्विस्टिंग. सो एनीवे अप्लाई योर कॉमन सेंस एंड जस्ट थिंक कि ट्विस्टिंग अभी नहीं चाहिए, सिर्फ अभी बेंडिंग चाहिए. तो बेंडिंग इसको लगाओगे तो बेंडिंग होगा, इट विल बी बेंड लाइक दिस. और ऐसे लगाओगे इसी प्लेन पे तो तब भी बेंडिंग होगा, ठीक है, जिसका डायरेक्शन कोसाइन है इस एंगल से कुछ नहीं होना चाहिए. तो या ऐसे लगाओ या ऐसे लगाओ या ऐसे लगाओ, बट ऐसे और ऐसे नहीं लगा सकते बिकॉज इट इज गोइंग टू शो यू ट्विस्टिंग कंपोनेंट. सो अप्लाई योर कॉमन सेंस एंड चेक आउट व्हाट ऑल आर द पॉसिबिलिटीज ऑफ दिस लोड. ओके, yes, the plane of loading intersects with the beam always. Excellent. Yes, you can say the plane of loading intersects with the beam. Exactly. Okay, are you getting the point or not? Tell me, Manjeet. Is it clear? Okay, so let's proceed further. So let me show you this vertical load, and due to this load movement will be generated. Can anybody tell me about which axis the movement would be generated? Can anybody tell me about which axis the movement would be generated? Tell me, guys. I want to hear it from you. I want to hear it from you, guys. Tell me about which axis the movement would be generated. Tell me guys about which axis the bending moment is going to produce due to this vertical load P. About which axis it is going to? Okay, yes. Okay. Sorry guys, sorry. Okay, Ashraf. Okay, Manjeet. Okay. Got it. So, Ashraf said, sir, it should be z-axis, and Manjeet said, sir, it should be y-axis. Manjeet said it should be x-axis. So, I am just telling you, dear, if you are applied load here, due to which what kind of a moment you are going to get? It is going to get the moment like this. Okay, for this load, it is going to bend like this. In order to prevent it, the moment will be generated like this. So this moment is about which axis? If I am going to apply, suppose if pen direction is x direction. This pen direction is x direction. If I am going to apply moment like this, then I will say it is moment about x axis. Suppose this pen direction is z direction. If I am going to apply moment like this, I will say yes, the moment is about z axis. Okay. Now due to this load P, bending will happen like this. Either ये स्माइलिंग फेस बनेगा या ये उदास फेस बनेगा. तो ऐसा कब पॉसिबल है? या तो आप इसको ऐसे बेंड करो या आप उसको ऐसे बेंड करो. So in both of these cases which are known as sagging and hogging, as we have seen it yesterday, so this movement we are going to apply about the z axis. About किसके about bending हो रही है? कौन सी axis है वो? Dear, it is z axis. Yes dear. Yes, Ashraf is again right. Yeah, it is about z axis. That's why we take delta mz is equal to 0 to calculate the reaction exactly. In all the planar structure, we take summation of mz is equal to 0. Okay. Yes. So it is z axis. So the very first thing which we have learned just now, that this moment is with respect to this diagram. I am saying with respect to this diagram, this moment is m is moment about z axis. ब्रैकेट में लिख देता हूं विद रिस्पेक्ट टू फिगर शोन. हो सकता है कोई और समझा रहा हो आपको और x को z को y कर दे, इंटरचेंज कर दे, बट हमारे डायग्राम के हिसाब से मूवमेंट किसके अबाउट लग रहा है? z एक्सिस के अबाउट लग रहा है. पहले मुझे बताओ ईमानदारी से, किसी को कोई डाउट यहां तक? यस, मंजीत इज राइट नाउ. किसी को कोई डाउट यहां तक? भाई बता दो एक बार. एनीबॉडी, एनी डाउट? पहला क्लियर हो गया. पहला क्लियर हो गया कि m कौन सी एक्सिस के अबाउट लग रहा है, m लग रहा है z एक्सिस के अबाउट which is perpendicular to our beam. In fact all these three axes are perpendicular to beam, but it is perpendicular to the board. It is perpendicular to the plane. It is perpendicular to the plane. It is perpendicular to the plane containing load. Okay. Now next thing dear. What about I? What about I? Tell me. What about I? Everybody. ये जो आपकी बेंडिंग होगी, जो आपका मोमेंट ऑफ इनर्शिया होगा, ये कौन से सेगमेंट को घुमा रहा है और कौन सी एक्सिस के अबाउट घुमा रहा है? आई नीड दिस आंसर फ्रॉम यू गाइस. आई नीड दिस आंसर फ्रॉम यू. टेल मी. व्हाट अबाउट आई? बताइए आई कौन सा होगा? टेल मी द एक्सिस. अबाउट विच एक्सिस? इज इट एक्स एक्सिस, वाई एक्सिस और जेड एक्सिस? अशरफ, टेल मी द एक्सिस. यस, वेरी गुड अशरफ. इट इज अगेन जेड एक्सिस. देखो डियर हो क्या रहा है, ये जो आपका क्रॉस सेक्शन है, ये जो आपका क्रॉस सेक्शन है जिसको मैं शेड कर रहा हूं लाल रंग से, दिस इज द क्रॉस सेक्शन. ओके, अंडरस्टैंड द बिहेवियर ऑफ दिस क्रॉस सेक्शन. बिफोर द एप्लीकेशन ऑफ लोड दिस क्रॉस सेक्शन वाज लाइक दिस. Before the application of load, this cross section was like this. Now what will happen after the loading? Now what will happen after the loading? This is your ZZ axis. Now what will happen after the loading? If this is the ZZ axis, so after the loading it will be going like this. It will be going like this. It will be going like this. Tell me if I am right. Okay, so it will be going like this, means it is bending like this. It is going to show you bending like this. So ultimately, if this plate is rotating, let's say this is a plate and this is the axis. If this plate is rotating about this axis, then I have to say that it is the moment of inertia about this axis, which is perpendicular to this whiteboard. Okay, which is perpendicular to this whiteboard. ठीक है, तो ये रहेगा यहाँ पे. तो it is again z axis. It is again z axis dear. Let me write it. ओके, अच्छा एक बात बताओ, फिर से क्वेश्चन. अगर ये लोड इसके बजाय मैं कह रहा हूं इसके बजाय अगर ये लोड आपका लगता कुछ इस तरीके से, लेट्स से अगर लोड आपका ऐसा लगता, नाउ द प्लेन कंटेनिंग इज x axis and plane of loading is you can say z axis. Okay, and it is perpendicular to x axis. Now what would have been the value of m, about which axis m is there and about which axis I is there? Tell me, about which axis m is there and about which axis I is there? Tell me guys, fast. Okay, great. And moment of inertia. Now it will be rotating like this about this vertical axis, and this vertical axis is y axis. It will be rotating like this. Are you getting the point or not? Tell me, guys. Are you getting the point or not? All of you tell me. Yes, here Manjeet has given us an important point. He said, sir, always take the axis which is perpendicular to the load. But ये बोलने में जिसको समझ में उसको आसान लगता है, it is not practical. I am taking load in the y-axis, okay, but both the axes are perpendicular. Z-axis is also perpendicular to y-axis, and x-axis is also perpendicular to y-axis. Okay. So first of all, we need to do this simple exercise जो मैंने अभी आपको करवाई. Then you can draw up to this conclusion that yes, exactly guys, exactly. चलो अब आप समझ गए हो, कोई बात नहीं, मेरी टेंशन खत्म. ठीक है. So this is the case here. This is my original case. Okay. Now next parameter. So ये दो चीजें समझ गए. I hope you all know that what is this IZZ. ये IZZ निकालना तो सबको आता ही होगा. ये IZZ निकालना तो सबको आता ही होगा. What is IZZ here? In this case, what is IZZ? If this is B, this is D, then it is BD cube by 12. It is BD cube by 12. And had it been a case of earlier one, green load one, then it is dB cube by 12. Okay. So IZZ for me is the moment of inertia about the axis about which bending is going to take place, and about which the bending is going to take place. That axis is also known as neutral axis. So neutral axis changes when the direction of load changes, when the nature of load changes. For bending, the neutral axis can be ZZ. For horizontal loading, the neutral axis can be YY, and for torque, the twisting is going to happen about x-axis, the neutral axis may be x-axis. So neutral axis can be anything. It can be ZZ axis, it can be YY axis, or it even can be your XX axis. Okay, it means a twisting or movement is occurring about which axis, or you can say neutral axis is also that axis about which the load is acting. Like here the load is MZ. So neutral axis is Z-axis. In another case, the load was happening about Y-axis. So in that case, the neutral axis is going to be Y-axis. In torque, the twisting you are going to apply about X-axis. Then the neutral axis is X-axis. Okay. So most of the guys are confused between centroidal axis as well as the neutral axis. Centroidal axis is fixed, but neutral axis depends upon the nature of load, upon the type of load, upon the orientation of load. I hope now this difference is clear to you. Yes, Manjeet, great. Yeah, okay. Now ये दो चीजें तो हमें अच्छे से समझ में आ गई. बस इसी को समझना है, हमने विजुलाइज करना है इस चैप्टर के अंदर, कुछ भी नहीं करना. अच्छा, अगला आता है सिग्मा. सिग्मा क्या होता है? Here you can see that although it is the outermost fiber, so it is having free rotation. But if I am going to take any interior fiber, so their strains are restrained. But if strains are restrained, then correspondingly the stresses will be developed. So if I am going to draw any cross section from inside, let's say this is my cross section. Again. यहीं पे बना देता हूँ. Confusion now. This is x-axis, and if I am going to draw this cross section again here, so it is like this. This is D. Okay. And how it is going to act, you can see that stresses at where do you think the stresses would be more? At the top fiber, at the neutral axis, or at the bottommost fiber, or any other point intermediate neutral axis and extreme fibers? Tell me where the value of stresses would be more, which will be generated due to this bending. Very good morning, dear Dinky. Tell me. So the neutral axis, at neutral axis, the bending stress is not going to occur. At this neutral axis, the bending stress is not going to occur. Okay, why? Because from equation as well you can see, if you want to write the equation for sigma, then it is simply m upon I into y. And before explaining sigma, let me introduce you what is y. Y is the distance from the neutral axis. Means suppose if you need to find neutral stress here, then y is this much distance. Suppose if you want to find the value of stress at topmost fiber, then y is simply your d by 2. If you want to find it at bottommost fiber, y is again d by 2. Okay, so y is the distance from the neutral axis, and you can observe from this equation that if y is 0, means at neutral axis there is no bending stress. Bending stress is increasing as you are increasing the depth of this y. As you are going away from your neutral axis, your bending stress increases. Okay, so m upon I is constant for a particular cross section. I is constant and m is also constant, and you can see that sigma is directly proportional to y. So that is the reason why this stress graph due to bending comes out to be linear. It comes out to be linear. So y is distance from the neutral axis. Let me write it here. Y is distance to fiber from neutral axis, where we need to find bending stress, and sigma is simply bending stress. Sigma is simply bending stress. Stress is developed due to bending moment, or you can say the stress function for sigma is m. Okay, so this is bending stress. So अगर मैं इसको बना के दिखाऊंगा, then how you can draw it? So it is going to be like this. Stresses are going, I am going to show these stresses like this. तो ड्राइंग की देख लेना, आई होप कि आपको समझ में आए. ओके, इस तरीके से जाएगा ये स्ट्रेस डिस्ट्रीब्यूशन. अगर एक सिर्फ फ्रंट व्यू देखना हो आपने, सो द स्ट्रेसेस वुड बी लाइक दिस. इसको ऐसे दिखा देते हैं. ओके, ओके ऐसे करना, समझने की कोशिश करो इसको, या फिर इसको साइड में ऐसे दिखा देंगे. इट इज सिंपली कैन बी ड्रॉन लाइक दिस. इट कैन बी सिंपली ड्रॉन लाइक दिस, दैट दिस इज योर बी. So this is your bending stress. So it is increasing as you are going away from the neutral axis. Okay, so that is the meaning of sigma. Okay, and you can see here, whenever there is a extension, what is happening? The top fiber for this particular case are in compression, and the bottom fibers below of the neutral axis are in tension. Actually they are expanding and contracting in the longitudinal direction. Although this normal force is indirect, it is developing due to bending, but they are expanding and contracting in longitudinal direction. So can anybody tell me which elastic constant we used for longitudinal direction? So for longitudinal direction, we take Young's modulus. What is Young's modulus? It is the ratio of longitudinal stress to longitudinal strain. So that is the reason why we are working in terms of Young's modulus here. So E is Young's modulus. Young's modulus of material. It is the Young's modulus of the material. Yes. Now what about R? Now what about R? What about R? Okay. R is, suppose if we do have beam like this. Suppose if we do have beam like this. Let me explain you like this. Suppose we do have a beam like this, and this beam is for loaded with some movement, like we have seen. Okay. So due to this, what will happen? It is going to show some elastic curve. It is going to show you some elastic curve. What is the shape of this elastic curve? Anybody? What is the shape of this elastic curve? What is the shape of this elastic curve? Tell me. What is the shape of this elastic curve? It is parabolic, circular, hyperbolic. Dear, all the analysis parabolic. No dear, it is not parabolic. Okay, it depends upon again on the type of load. In simple bending equation, I can write one more assumption. Equation is for pure bending. Equation is for pure bending. Equation is for pure bending means only bending moment is developed. Although we are using this equation even in case of non-pure bending, but originally this equation is derived for pure bending. Okay. So if it is a case of pure bending, dear, then what is happening? Then this curve is coming out to be circular. I will tell you why this is circular. Because we know that M upon I is equal to E by R. This R is the radius of curvature. If this is my center, then this is the value of R. R is the radius of curvature. And you can see if bending moment is constant, then what is R? R is E, I upon M. For prismatic beam we are doing, so I is constant. Young's modulus, same material, E is constant, and in case of pure bending, your bending moment is not going to change, M is also constant, so R is also going to be constant. And if R, that is the radius of curvature, is constant, it can happen only in a circle. So in case of pure bending, we take the elastic curve as an arc of a circle. You can also make it as a note, dear. In case of pure bending, the radius of curvature is constant. That's why the elastic curve is taken as the arc of a circle. Okay. Yes, क्या बात है ऋषिकेश, आ गए? एनर्जी क्या, बस जो थोड़ा बहुत है वो बता देता हूँ, जो थोड़ा बहुत जानता हूँ बता देता हूँ आपको. Is it clear, Ashraf? Yes, circular for this theory. It is the circular for this theory. So this is the R, and you can see more is the R, lesser is the curvature. Smaller circle will be having more curvature than a bigger circle. So bigger circle is going to have less curvature. Smaller circle is going to have more curvature. Means less R means more curvature. More R means less curvature. So that is the reason why you define that curvature of the elastic curve is inversely proportional to R. So where K is the curvature, it is the curvature, and curvature is inversely proportional to radius of curvature. Curvature is inversely proportional to radius of curvature. है ना, ज़्यादा radius मतलब curveness कम, flatness ज़्यादा. Like you can see the case of Earth. Here the curvature, radius of curvature is huge, 6400 kilometer, and still you can feel. That's why you are feeling that on the surface which you are surviving is flat. Are you getting the point or not? Okay, so R is the radius of curvature. Let me write it down here. R is the radius of curvature. So this is the basic simple bending equation. This is the simple bending equation. Okay. So like this we are going to work. So M upon I is equal to sigma by Y is equal to E by R. I hope now each and every points are clear. Okay. Degree of curve is K. ऐसा है क्या सर? Yes, degree of curve is no, degree of curve is K. You cannot say like this. Degree of curve depends upon its mathematical function here. What is the degree of the curve? Okay, 2 degree are also parabolic, 2 degree are also circular, 3 degree are cubic parabolics and all. Okay, degree of curve is not curvature. Curvature means how rapidly your tangents are varying. How rapidly your tangents are varying. Okay, how rapidly your tangents are changing. So that is the curvature. कर्वेचर देखो ना, ये है आपका, यहाँ पे आपको देख के लग रहा है कि अगर आप इस फ्लाईओवर पे चढ़ोगे तो आपको देख के लग रहा है कि आपको दिक्कत ज़्यादा होगी, और एक ही आपका ये है, यहाँ स्मूथनेस ज़्यादा है. सो इफ यू आर गोइंग टू कंपेयर बोथ ऑफ दिस देन कर्वेचर इज मोर हियर. कर्वेचर इज मोर. डिग्री ऑफ कर्व में ना आप मैथमेटिकल डेफिनेशन भी दे सकते हो. हियर कर्वेचर इज लेस. व्हाई इट इज लेस? बिकॉज रेडियस इज मोर हियर and here radius is less. Are you getting the point? So curvature and radius of curvature are inversely proportional. It is like that. So we cannot say it is directly degree. Okay. You can say the rate of change of curveness is known as curvature. If this rate is more, it means curvature is. ना ये आप सर्वेइंग में, हाईवे डिजाइनिंग में भी, सेटिंग आउट ऑफ कर्व में भी ये कंसेप्ट यूज करते हो. आपने देखा होगा कि मोस्ट ऑफ द फ्लाईओवर्स आर टेकिंग ह्यूज रेडियस ऑफ कर्वेचर सो दैट द फोर्स, द सेंट्रीपिटल एक्सेलरेशन व्हिच यू आर गोइंग टू गेट इज इन द परमिसिबल लिमिट. ओके, इज इट क्लियर? चलिए, सो दिस इज द केस हियर. So this is the bending equation, simple bending equation, and you know that how to calculate this normal stress now, how to calculate the bending stresses, how to write the bending moment equations. We have already seen that. And now after this bending equation we introduce one more term which is known as a section modulus, which is known as section modulus. Anybody, what is section modulus? Actually the sigma is coming out to be m upon I into y. Okay, so for extreme condition this y tends to y max, m upon I into y max, this y tends to y max, and here you can see that this sigma is m upon y over y max. So this is known as z, and it is defined as I upon y max. Y max is nothing but the maximum distance to the neutral axis. Okay, geometric property of the beam which defines the strength is known as the beam section or section modulus. Yes, so this z is I upon y. You can see that m is directly proportional to z. M is equal to sigma into I by y max, so it is z. So if z is more, then moment carrying capacity of the section is more. So ultimately section modulus is the tool in bending which is which can do the comparison due to bending moment. A section, a cross section which will be having more section modulus, you can say that yes, this particular section is going to behave good in bending. For greater load it is going to deflect less. For greater load it is going to give more moment of inertia. More z means more moment of inertia. If moment of inertia of a section is more, it means moment of inertia is the rotational analogous of mass only, means it is having more inertia. So more heavy mass, it is difficult to move on. So more I is difficult to rotate on. Are you getting the point or not? So Z is your section modulus, and it is giving you the strength of the beam in bending. It gives the idea of strength of cross section in bending. Okay, you all know how to calculate. I hope you all are familiar with the parallel axis theorem and perpendicular axis theorem. Although here the parallel axis theorem will more used, in torsion you use perpendicular axis theorem more. What is y max? I hope you also know. If the section is symmetrical, then y max you are going to get same on either side. Okay, suppose if I am having some uniform section like this. In this section, if I ask you what is y max, then you will be saying, sir, it is y by 2, it is d by 2. Doesn't matter if you are going from upside or you are going from downside. It is same. It is same. Here as well it is d by 2, and here as well it is d by 2. But in case of non-symmetrical section, like in case of triangle, what is going to be the value of y max? What is going to be the value of y max? What is going to be the value of y max? It is d by 3, and it is 2d by 3. So here you have to take value of y max as 2d by 3. Okay. So as Ashraf said that it is the geometric property of the beam which defines the strength of the beam, but we could have add one more word here, in bending. Okay. So Z more Z मतलब क्या होगा कि बीम आपका बेंडिंग में ज्यादा स्ट्रॉन्ग है. So whenever we have to compare the beam movement carrying capacity of the section, so directly we can find out the Z value of the different section. The section which is going to have more Z, it is capable of taking more bending moment with less deformation. Are you getting the point or not? For example, if I give you the section modulus of some standard geometries, section modulus of some standard cross sections, then what is going to have circle का क्या होगा section modulus? Anybody? Circle का section modulus क्या होगा? Let's suppose the diameter of circle is d. So what is the section modulus? इसका diameter मान लो d, तो यहाँ पे जो z लिखोगे that is equal to pi d cube by कितना होगा? It is pi d cube by 64, इसका हो गया d by 2, और it is area into d square by area into d by 8, area into d by 8 है ना. Suppose if I am taking the normal rectangle, then what will happen? अगर normal rectangle लेता हूँ मैं, okay, suppose if this is B and one is D, so this is B and this is D. So what is this Z? Z is going to be BD cube by 12 divided by D by 2, because it is also symmetrical. So it is BD square by 6, or we can say it is area times of D by 6. It is area times of D by 6. So we can say like this. Please let me know for any doubt. And triangle की बात करूँ तो what about triangle? Triangle में कितना होगा डियर? What will happen in triangle? It would be BD cube by 36 into 2h by 3, because y max is 2h by 3. It is BD d cube by 6 or bh cube. If this is b, this is h, it is bh cube by kitna 36 into 2h by 3. So if you are calculating this, it is bh square by 24, or it is area into h by 2. It is area into h by 2. Okay, got it or not? Tell me. Okay, and these all are the section modulus of some standard cross section, and you can find it for composite section. All you need to know how to use moment of inertia, how to use the parallel axis theorem, you know how to calculate the CG of the composite section, because then only you will be able to calculate Ymax, and then only you will be able to shift the moment of inertia of individual section about that particular axis. Okay, so like that you guys can find the section modulus of standard cross section as well as your composite cross section. Okay, tell me any doubt to anyone? Tell me. Okay, so what I want to conclude there, that flexural strength depends on depends upon Z. Okay, and Z is again depends on moment of inertia. Okay, is it clear or not? Okay, so we can say I how we can say that I value is going to be more. अगर मैं कहूं कि मेरे पास यार एक फिगर ये है और मैं कहूं मेरे पास एक फिगर ये है, then out of these two figures where the moment of inertia is more? It is more. What is moment of inertia? It is the area into r square. Here you can see that r is more away from the neutral axis and more area is present here, and here you can see r is this, and as you are going away the area is reducing. So this value is becoming low, this value is becoming low, all of you. So here the moment of inertia would be less, here the moment of inertia would be low. So such diagrams are more useful from bending point of view. That is the reason why we are using the flange section. Wherever we need to resist more bending, there what we are doing, we are providing the flange section. Means the purpose of providing flanges is that to increase the area of the section as you are more away from the neutral axis, because these particular portions are going to give you huge moment of inertia. Okay, so we can say this, we can conclude from here that for given y z is more if I is more, and I is more if more area is located away from the neutral axis, Okay, so that's why we can say indirectly it is the moment of inertia only which is defining the strength of the beam in flexure. Okay, it is the strength of the beam in tension. Are you getting the point or not? Everybody tell me, are you getting the point or not? So yes. Okay dear, so now we can move on to, based on this concept, we can move on to a small numerical. So numerical is a objective question is there for you guys. I hope you all will attempt this. Okay, so a beam with the positive cross section given is subjected to a positive bending moment which is causing compression at top, and of 16 kilonewton meter acting around the horizontal axis. Now what is the tensile force acting on the hashed area? What is hashed area? Let me draw it. So tell me the value of tensile force acting in the hashed area. Okay, so this is the uniform section, and you can say that this is the neutral axis. You can say this is the neutral axis. This is your neutral axis. So just tell me the value of tensile force which would be resisted by this hashed area here. Okay, tell me. So first of all, we can draw the stress diagram for this. What is the stress diagram? What is the value of this extreme stresses? What is the value of this extreme stresses? Let me know. So this is coming out to be, अरे कैलकुलेटेड नहीं है, बस फील देने के लिए एक न्यूमेरिकल मैंने आपको दे दिया, 100 into b d cube by 12. So the stress is coming out to be 42.67, 10 into 10 to the power 6 bd cube by 12 into 75. Okay, yes, so it is coming out to be 42.67, and this stress is coming out to be divided by 75 into 25. It is coming out to be 14.22. So if we want to find stress here, okay, force here, then tensile force here would be area of this portion into average stress. So average stress in hatched area, average stress in hatched area, it is going to be how much? Average stress in hatched area, it is going to be 14.22 divided by 2, and tensile force in hatched area is average stress multiplied by area. Area is 50 into 25, so this is 50 into 25. It's coming out to be 17777.7 Newton. Okay, so you can keep it 17.8 kilonewton. So this is the way to calculate such numericals. Okay, so here it is going to be 17.8. It is going to be 17.8. It is going to be 17.8. Okay, chaliye. So this is the way here. This is the way to calculate. Now next. So this is you can say about bending, although you can also see some standard results like tapered beam and all. Okay, but they are not very much required. So all these things were needed for your building of concepts. I hope these theory of bending, theory of pure bending is quite clear to you. Anybody, any doubt? कोई डाउट हो तो पूछ के चलिएगा, कोई डाउट हो तो पूछ के चलिएगा. Okay, so I would like to move on to the next topic here. पहले क्या करोगे, टॉर्जन या शियर? पहले क्या करोगे, टॉर्जन और शियर? टेल मी. टॉर्जन उठाए, टॉर्जन उठाए. Okay, so let's start with the torsion. So टॉर्जन इसलिए उठाने का मेरा मन था, और देखो आप सीक्वेंस में भी आप देखोगे तो जस्ट आफ्टर द सिंपल बेंडिंग आई हैव केप्ट टॉर्जन बिकॉज रिजेम्बलेंस इज वेरी वेरी हाई इन आवर सिंपल बेंडिंग एंड इन टॉर्जन, है ना. यहाँ पे रिजेम्बलेंस दोनों में जो है वो काफी ज्यादा है. ठीक है, टॉर्जन में डियर व्हाट वी कैन डू, वी कैन अप्लाई द सिंपल टॉर्जन इक्वेशन. Just it is very very similar to the simple bending equation. Actually it refers to the if I am starting with the torsion of especially the circular bar or circular shaft, then I can say that torsion is simply refers to twisting. It simply refers to twisting of straight bar. Twisting of straight bar when it is loaded by torque that tend to produce rotation about longitudinal axis of bar. It is just like suppose we do have some shaft, maybe like this. Let's suppose this is a shaft. Okay. क्या हो गया? अरे 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 क्या हो गया भाई? इतना गुस्सा. So you can see, suppose if this end is fixed, and you are going to apply some twisting moment here. So what would happen about this longitudinal axis? This is your longitudinal axis, and this time this longitudinal axis is going to work as the neutral axis. So this is going to be the angle of this is the axis of shaft, and this time these cross section, let's say it is A, it is B, it is C, it is D. These cross sections are going to, these points on the cross sections are going to move. So A will come somewhere here, B will come somewhere here, C will come somewhere here, D will come somewhere here. So they will be going like this. So simply you can see that if this is a B, C, D before twisting, after the application of torque, now A, this is the initial you can say scenario, and after twisting the scenario is going to be like this. A will be rotated by, if theta, then B, C, D will also be rotated by theta. Then B, C, D will also be rotated by theta. So you can consider all of these angles same. This is A dash, this is A, revised position of A. This is revised position of B, this is revised position of C, this is revised position of D. So they all can move. They all can move. Are you getting the point or not? Okay. क्या वो लैग ज़्यादा चल रहा है क्या? Is it lagging much? Okay. So that is the case. So this is known as the torque. And what is pure torsion? When your section is only subjected to torque and no bending, no axial, nothing else is happening, then the situation is known as pure torsion. So pure torsion refers to only twisting moment or torque to shaft. Only twisting moment or torque to shaft. Are you getting the? It is not accompanied by neither axial force nor bending moment. So write it down here. Not accompanied by axial force and bending moment. Not accompanied by axial force and bending moment. Okay, are you getting the point or not? So the simple torsional equation which we are going to use is this much. You can see its resemblance with the simple bending equation. They are very much resembled. Okay, so minor distinctions are there that I am going to tell you in the meanwhile. So simple bending we just have seen, it is m upon I. It is sigma by y is equal to E by R. So torsional formula you can see, it is a T upon I. T is going to happen about the longitudinal axis. Let's say it is Tx. I is also about the longitudinal axis. Okay, with respect to diagram. What is longitudinal axis? Let me call this axis as longitudinal axis. Let me call this axis as longitudinal axis. It is x. Okay, let's say it is y. Here the y and z are symmetrical. Let's say this is z. Let's say this is z. This is y. This is x. So this is the scenario here. So T upon I is equal to tau by R is equal to G phi by L. Okay, Tx is torsional moment about x-axis. Ix is also known as Ip, or some in references it is written as J. It is known as polar moment of inertia. It is known as polar moment of inertia. Generally we used a perpendicular axis theorem to calculate polar moment of inertia if it is not a standard case. Now, like we had in simple bending equation sigma, which is the bending stress due to the bending moment, similarly here tau is known as the shear stress. Here tau is known as the shear stress. It is the stress developed due to the torsional moment, due to the twisting. So it is shear stress due to the twisting. Like we had y as the distance from the neutral axis, similarly r is also the distance from the neutral axis, or you can say it can be any local radius where we are interested in finding the shear stress. Okay, as we have same stresses at the same y, similarly we are also going to have same kind of normal shear stresses at a constant r. Means a cross section, the outer, in circular cross section, the outer fibers are going to have same sort of stresses. Then again this circle is again a locus of point where you can find the same sort of shear stresses. Okay, so same R means same stress, like we used to calculate same Y means same normal stress. G is shear modulus, as the shear involvement is there. Here the tangential movement is there. So instead of Young's modulus, here they have used shear modulus. Phi upon L is angle of twist per unit length. Now what is angle of twist per unit length? This is also important to understand. We cannot define the degree of torsion only on the basis of phi. It is actually how much phi is happening with respect to the longitudinal line. That is only going to give you the relativeness of torque. Suppose I can have two bars. Let's suppose this is my bar number 1 and let's suppose this is my bar number 2. This is my bar number 2. So you cannot say now that in bar number 2 the angle would be this much, and if bar number 1 is angle would be this much, then more torque would be here. It is depending upon how much this angle is there with respect to length. So let me be more specific. Let me keep the cross section even same, then you can understand it in a better way. Let me draw two figures one more time. Now you will be able to understand this. This phi is the angle of twist which you can have in the cross section. Let's suppose if we want to know the value of phi here. So phi here is 15 degree over 15. So it is 1 degree per unit length. Here if you want to calculate phi, it is coming out to be 10 degree over 8. So it is 1.25 degree per unit. Although the angle is looking more here, it is looking out to be 15 degree, but the fact is that torque is more here, because in a less length more deformation have been taken place. If you are talking about the relative shear, then you can say this much 15 degree has happened over a length of 15 meter. Here it is 0 and here it will reach till 15. But here the angle of twist is more, it will be considered more because it is with respect to the length. So the degree of torque is more in case number B. So therefore only solely based on the value of phi we will not be able to judge that which torque or which shaft is subjected to more torsion. So it depends upon phi per unit length. It is like phi per unit length. Okay, so that's why phi by L we have seen. G is shear modulus and phi by L is angle of twist per unit length, per unit longitudinal length. So let me write these as well. It is a shear modulus or modulus of rigidity, shear modulus of rigidity, and phi by L को मैं एक साथ define कर देता हूँ. Phi by L is angle of twist per unit length, angle of twist per unit length here. Okay, so it is the angle of twist per unit length. So please let me know if you guys are having any doubt. Okay, and most of the assumptions are same in torsion as we used to have in simple bending equation. Okay, so if you want me to write the assumptions, then quickly I can write it for you guys. So assumptions involved in torsional theory. The first one, plane section before torsion will remain plane after torsion, or you can say that circular section is going to remain circular only. like we used to had plane section before bending will remain plane after bending in simple bending equation. So here it is circular section remain circular, circular section remain circular. Okay, what else anybody? और क्या हो सकता है? Okay, section is not going to warp, section is not going to warp. I hope you all know understand what is warp. What is warping actually? What is warping? Anybody? What is warping? So due to this what will happen, this is a plane and it's going to remain plane even after the torsion. It is not going to happen that if a plane containing A here, B here, C here, and on the next time whenever you are drawing a revised plane after torsion, so A, B, C, they are not lying on the same plane. If the longitudinal displacement is happening between A, B and C, if the displacement along the longitudinal axis is happening about the A, B and C, okay, in such a manner that A, B, C are not in the revised plane now, then the section is subjected to warping, which is very much common in non-symmetrical section like even triangular or circular shaft and all. Okay, so section is not going to warp. This is again an assumption here. After this you can say that the shaft is loaded by twisting couple. Shaft is loaded by torque only, means it is not going to accompanied by axial force or bending moment, so we can handle only torque at a time. Okay, although the methods are there by which we can convert bending and torque into an equivalent manner. After that they are not going to exceed the proportional limit, means here as well your Hooke's law is valid. So stresses are not going to exceed proportional limit. They are not going to exceed the proportional limit. Okay, so these all are the assumptions involved here. These all are the assumptions involved. So polar moment of inertia, how we can calculate this is the basic portion of the mechanics. Okay, after that you simply have to use this simple torque equation or simple torsion equation in order to calculate the shear stresses at any section. Okay, but one thing I would like to show you that how these shear stresses are going to work. Suppose we have a section like this. Please try to understand this. Let's suppose this is a section. Okay, okay. And suppose this is a center and I'm showing it like this. Okay, so this is the case. Now, if this is located at a distance r and this is located at a distance r, so how shear stress is varying? We know that tau is equal to T upon J or IP into R. So for a section, torque is constant, for polar moment of inertia is also constant. So we can say that this torque is directly proportional to R. So as we are going away from the neutral axis, as we are going away from the center, the value of shear stresses is increasing, and it is increasing like this. Let me use red color for this. So about this, it is going to increase like this. But shear are happening. You know about shear stress, we saw it yesterday, that they act equal and opposite onto mutually perpendicular plane. If one plane is going to have tendency of going into the clockwise direction, then just to maintain the moment equilibrium, the other side is going to show you the anti-clockwise direction. So this one is going to be like this. So this one is the longitudinal stress. This one is the longitudinal shear stress. This one is the longitudinal shear stress. And this one is the transverse shear stress. This one is the transverse shear stress. Are you getting the point or not? Okay, so they are linear not only across the cross section, they are also linear in the longitudinal shear stress. Then only the moment equilibrium would be maintained. Then only the moment equilibrium would be obtained, my dear friends. Are you getting the point? So like that, we can show you the shear stress variation due to torque. Okay, please remember, only in case of torsion of a circular shaft, this shear stress distribution is coming out to be linear as you are going away from the center line or neutral axis. But when we will be discussing shear stress due to the vertical force or due to the transverse force, so there the nature of shear stress distribution will be different. Here it is linear and there it can become parabolic. Okay, so don't be confused. So due to torque, its distribution is linear. Due to transverse force, which we have to see further, it is going to be parabolic in nature. Okay, so don't be confused here. Okay, and you can also use the pure shear theory, and you know that in pure shear condition the failure is going to happen about 45 degree. So you will be able to locate the possible positions of cracks, and accordingly you can find the means. In short, if I want to take any member here, suppose if I want to take any member here, so this is your you can say that it is going to happen like this. It is going to happen like this. So it is going to elongate in this direction like this. I hope you all are getting it correctly. I hope you are getting it right. Okay, so this is like they are going to fail. So accordingly we can provide the reinforcement and all. Is it clear to you? Okay, so let's start connections or bars. Before starting this, I want to introduce the sign convention. For sign convention, we are going to use the right hand thumb rule. It's very simple. Like if torque is going like this, so my thumb is outside. So I am going to show about axis this kind of torque towards right hand side. If the torque is like this, my thumb is toward this side, so I am going to show torque like this here. Okay. If I am going to do use the same, then similar results would be obtained as we had in axially loaded member. Okay, that outward axial load you can take tensile positive, and inside you can take compressive or negative. So there A and E were going to play a role. Here G and IP are going to play a role. There AE was the yes, A and E was the axial stiffness. They are giving the idea about axial stiffness. Here G and J are going to deal it. Okay. So what is going to happen now? Let's see. So first of all, this we can say that it is the bar in series. It is the bar in series. So suppose if I want to draw it again. Suppose if I want to draw this segment again, then this is one portion. Consider it circular, huh? And this is second portion. And this is the third portion. In fact, there are two segments. B to C is different and C to B is again different. Okay, B to C different and C to B is again different. And this is your third point. So you know how to show these forces. So first one you can show it like how? You can show it like right hand thumb rule. It is going outward. Show it with double arrow, otherwise you may be confused between this and axial load. Okay, and this is your TB. TB is coming in. TB is coming in here. TB is coming in. Okay. First of all, let me draw it like this. So TC is going again going in, and this is going towards right hand side. Okay, so like that we can calculate. Okay, so now if I am going to draw the equilibrium, so this is only subjected to TA. So AB portion is only subjected to TA. So this AB portion is only subjected to TA here. This is only subjected to TA. Next is BC portion. Let me draw that. BC portion is like this. Here you can see TA is coming down, TB is coming down and TA is coming out. So you can show it with TB minus TA. You can show it like TB minus TA like this. Next is this is your AB, this is your CB. Now on next page I am trying to draw DC. So how DC is going to vary? How DC is going to vary? So simply you can see TA is going out, TB is coming in, TC is coming in. So it would be like this. It would be like this. TB and TC are coming in, but TA is going out. TB and TC are coming in, but TA is going out. So like this I can show. So this also from equilibrium point of view. It is TB plus TC minus TA. TB plus TC minus TA. Okay. Now the last segment is DE. DE अगर मैं बनाऊंगा तो it will be like this. And here you can also have one torsion equilibrium equation. You know the torque which is coming at E is equivalent to TE. So you can also say that your TE is also equal to TB plus TC minus TA. This is one equation. Okay. What else information you can use here? What else you can use here? So bars in series, what else you can use here? You can say the change of angle between E and A is equal to the change of angle between ED plus DC plus DCB plus BA. So change of angle between E and A is equal to the change of angle D with respect to E plus C with respect to D plus B with respect to C plus A with respect to B. So this is the compatibility which you can use here. Not compatibility, this is the fact you can use here. Compatibility it would be when it is a case of indeterminate bars. Okay, where the change of twist angle between two fixed supports are equal to 0. So in case of indeterminate structure, you can draw compatibilities out of here. Are you getting the point or not? So here you can say the theta A minus theta E. Here you can say here my theta A minus theta E is going to happen due to, it is going to happen due to theta A minus theta E. They are going to happen due to, which is nothing but theta A minus theta E is equal to this is theta A with respect to B plus theta B with respect to C plus theta C with respect to D plus theta D with respect to E. So how to calculate theta A with respect to B? It is subjected to TA L upon GJ1. Okay, this is the way of calculating theta, na? So we know that T upon J or IP is equal to G theta by L. So it is theta is what? TJ TL upon GJ. So it is TJ upon how much? TL upon GJ, J of this or IP of this, L of this, T on this. What is T? TA. Whenever you are computing the same for theta B to C, so what you can write? It is due to, in place of T you have to write TB minus TA. L is of length BC. Okay, J of section cross section cutted between B and C. Okay, so it will happen like this. Okay, it is going to happen like this. So same you can use it as a equation. Okay, and what is the thing which is common when the bars are in parallel? Suppose I do have two bars here. This is the outer tube, this is the inner tube. So what all are the things which are common here? Anybody? Bars in parallel. The total applied torque is going to distribute into two members. Suppose this is member number 1, suppose this is member number 2. The total torque is equal to T1 plus T2. And the common thing here is this, that theta angle of twist is same. Angle of twist is same. So theta of first material and theta of second material are same at a cross section. So this you can use as a compatibility. You know what is theta 1? It is T1 L1 upon GJ1 और GIP1, JIP जो भी यूज करना है कर लेना भाई. Okay, it is T2 L2 G2 J2. Generally in parallels the length are same. Okay, if you are knowing the G and of the material and you know the dimensions of the material, then you can also calculate the polar moment of inertia. So accordingly you guys can calculate, accordingly you guys can even calculate here. Okay, so GJ is torsional rigidity. Okay, and AG is shear rigidity. EI वहां पे पढ़ा था flexural rigidity. AE आपकी axial rigidity. So all these are the various rigidity. 4 types of rigidities exist here, which you need to know in strength of material. It's one is for shear, one is for indirect shear, which is torsion, one is for axial, another is for indirect axial, which is bending. Okay, are you getting the thing or not? Are you getting the concepts, my dear friends, or not? And here as well you guys can deduce the relation for bars in tapered beams, composite sections and all. Okay, कोई डाउट किसी को यहाँ तक? So this is the key point to solve indeterminate structure. Okay, and yes, one more thing you can use. What is the power transmission? Power के भी क्वेश्चन आते हैं. So power transmission in a circular shaft. What is that? क्या बात है ऋषिकेश, आ गए फिर से? कंसेप्ट किंग हो सर जी आप. अच्छा बेटा, ऐसा लगता है नींद से उठ के आते रहते हो, बीच में एक तारीफ करते हो फिर चले जाते हो. पावर ट्रांसमिशन क्या हो जाएगा? P इज इक्वल टू क्या होता है? जैसे पावर को हम लोग डिफाइन करते हैं अपने फिजिक्स में रेट ऑफ चेंज ऑफ वर्क डन, एनर्जी पर यूनिट टाइम. वर्क डन इज द डॉट प्रोडक्ट ऑफ फोर्स एंड डिस्प्लेसमेंट एंड इट्स रेट इज गोइंग टू बी F डॉट V. सो अगर लीनियर में हमारा पावर इज द डॉट प्रोडक्ट ऑफ फोर्स एंड वेलोसिटी है, तो व्हाट इज एंगुलर का फोर्स? इट इज टॉर्क. What is angular key velocity? It is angular velocity omega. So similarly we can define the power transmission, which is rotating with some angular speed omega, but here the speed must be constant. Okay, then power transmission is given by, it is the dot product of torque and omega. Simply tau T into omega. Why dot product I am writing simply T into omega? Because angular velocity is always its direction is perpendicular. Okay, are you getting the point or not? So T into omega is going to give you the power. Okay, so omega generally it is in a revolution per minute or per second you need to calculate. T is the torque. Okay, so we can use it like this. ठीक है. नॉन सर्कुलर मेंबर आई एम नॉट टेकिंग डियर. ठीक है, चलिए. So this is about your you can say torque. Now the next thing which we can take up here is shear. So shear थोड़ा सा डिस्कस कर लेते हैं और shear के बाद फिर सेशन क्लोज करते हैं और फिर बढ़ेंगे अपने अपकमिंग टॉपिक्स के ऊपर. ठीक है, तो shear के लिए हम बात करें, आधे घंटा और लेते हैं, shear को ख़त्म करते हैं अच्छे से. ठीक है, and it is also important here. Direct results I will be using here. Okay, so although अभी भी जो आपने किया वो भी shear था, but that is an indirect case of shear and it is happening due to the shear stress or torsional moment. ठीक है, ये काम करते हैं डियर, काम करते हैं. जस्ट लेट मी हैव 5 मिनट ब्रेक, थोड़ा सा मैं रेस्ट ले लूँ और 5 मिनट में स्टार्ट करते हैं और फिर इसको आधा पौना घंटा लगातार खींचते हैं. ठीक है, So I am coming in 5 minutes. 12:55 पे I will be back. Okay. So मैं जब तक स्ट्रीमिंग स्टॉप कर रहा हूँ, तो don't think it is going to be buffer and all. I am stopping this streaming. Okay. So I will be back in 5 minutes. देखते हैं हम लोग एंड दिस टाइम वी आर। अच्छा, अशरफ जी कह रहे हैं सर शेयर सेंटर के कंसेप्ट से थोड़े से क्वेश्चन करवा दो, कुछ ज़्यादा जान सकते उस कंसेप्ट से। शेयर सेंटर मैं कवर करूँगा, शेयर सेंटर मैं कवर करूँगा अपने नेक्स्ट सेशन में, जो भी 2 बजे से है, बट 2:15 से आई विल स्टार्ट दैट सेशन। तो शेयर मैं उसमें कवर करूँगा। हाँ, चलो तो करते हैं स्टार्ट शेयर का। तो शेयर इज बेसिकली अभी भी जो हमने किया वो शेयर किया, बट दैट टाइम इट इज ड्यू टू दी टॉर्क। एंड प्लीज कीप वन थिंग इन माइंड कि इफ यू आर अप्लाइंग बेंडिंग मोमेंट, ड्यू टू दैट नॉर्मल फोर्सेज आर कमिंग, नॉर्मल स्ट्रेसेस आर कमिंग, एंड ड्यू टू ट्रांसफर्स लोडिंग योर शेयर स्ट्रेस डेवलप्ड इन योर सेक्शन। सो इसी शेयर स्ट्रेस को हमें पता लगाना है कि व्हाट इज द नेचर ऑफ दिस शेयर स्ट्रेस डिस्ट्रीब्यूशन along the across the cross section or along the cross section. ठीक है। So one thing you can write that normal stresses are produced by bending moment. Let me write it down. And your shear forces and your shear stresses are produced by transverse forces, or you can say shear forces. Okay, so this is the concept here. Okay, so dear, how we can write the shear? For that we do have one general equation. Suppose if we have any rectangular beam, and इस rectangular beam के cross section मैंने आपको बनाया, और यहाँ पे अगर मैं देखना चाहूँ कि at a distance y how much shear stress is being produced, for that we have equation here. That equation is like tau. If tau is the shear stress, then tau is equal to V over IB into area into y bar. We need to understand कि V क्या है, I क्या है, B क्या है, A क्या है, y bar क्या है। V is shear force। जिस भी सेक्शन पे, सपोज मैंने यहाँ पे सेक्शन काटा, तो जिस भी सेक्शन पे आप shear stress का एनालिसिस कर रहे हो, तो वहाँ पे लगने वाला जो फोर्स है, वहाँ पे लगने वाला जो रिजल्टेंट वर्टिकल फोर्स है, दैट इज द shear force V. I is neutral moment of inertia about the neutral axis of the entire section. B is the width of the section, like this is the width of the section. Okay, A is the area above this y or below this y till free surface. So normally we do have a practice of taking analyzing smaller section. So A is this is the A. अगर आपको EF लेवल पे shear stress निकालना है, तो इस लेवल के ऊपर से लेकर के फ्री सरफेस तक जो एरिया कैप्चर होगा, दैट इज योर ए। एंड इसी एरिया का जब आप मूवमेंट लेते हो अबाउट द न्यूट्रल एक्सिस, दैट इज नोन एज वाई बार। एरिया इंटू वाई बार इज द कंबाइंड टर्म। ओके, सो बट वाई बार इज जो आपने एरिया कैप्चर किया है उसके CG तक का डिस्टेंस फ्रॉम योर न्यूट्रल एक्सिस। ओके, so you can see here that I have written all the terms here. Shear stress at any point P distance y from neutral axis is given by tau or Q in some of the books, and this is V over IB into AY bar, where V is the shear force at section, A into Y bar is the movement of the shaded area. Here this is the shaded area, red one, about the neutral axis. I is the here as I mentioned, A into Y bar area of cross section, or A is the area of cross section above EF. Yeah, A is the area of cross section above EF till free surface, okay, till the outermost fiber, and Y bar is the distance of centroid of area A from the neutral axis. I is again the moment of inertia about the neutral axis, and B is known as the width of the section where we need to find the shear stress. In rectangular beam, I beam, generally widths are not varying, but these widths are continuously varying in case of your circular section, in case of your triangular section. So in all such sections your widths continuously varies. Okay, so एक आपको बना के दिखा देता हूँ फॉर रेक्टेंगुलर केस इफ वी आर डीलिंग. सो टाउ इज रिटन एज v over ib into a y bar. So what is a? For same cross section अगर मैं बनाऊं, so this is b, this is d, this is the neutral axis. Okay, this is the neutral axis. This is let's suppose a distance where you want to know shear stress, and above to this is the area under consideration, which is responsible for inducing shear force at this level, or this area you can also say. But as I told, we always have a habit of analyzing lesser area. So green one I am taking. So this is d by 2. सर सोम को काफ़ी इम्पोर्टेंट सब्जेक्ट है गेट के लिए, लेकिन फिर अटेंडेंस क्यों कम है सर? स्टूडेंट्स लाइव आते ही नहीं. Maybe they are good with their preparation, I don't know dear. Okay, so what is the value of y bar? I think multiple times हुआ भी है ना, और there may be some parallel sessions which is more important. Okay, ऐसा भी हो सकता है because the SOM is running quite a time here. कई बार इसको करवाया गया है. So this is my y, and what is y bar? Y bar is the CG of this area. Y bar is CG of this area. So it is y plus d by 2 all divided by 2. And what about area? Area is b into this remaining distance is how much? It is d by 2 minus y. Okay, so if I want to collectively obtain the value of ay bar, it is b d by 2 minus y into d plus 2 plus y by 2. So it is coming out to be b by 2 into d square by 4 minus y square. So now if I want to write the equation of shear stress, so it is v over I you can also write like this. Ay bar we have already calculated. Six v upon b d cube over d square by 4 minus y square. So this is the mother equation for rectangular beam, and it will be used for plotting the shear stress distribution. As you can see here the degree of y is 2, so this variation is going to be parabolic in nature. ये जो variation आपका होगा it will be parabolic. So if I want to plot this function, If I want to plot this function, then you can see at y is equal to 0 means at neutral axis the value is 3 by 2 v over bd, and at extreme fibers when y is equal to d by 2, so y square will be d square by 4, it will be cancelled. So shear stress distribution at topmost fiber and bottommost fiber due to the shear force is coming out to be 0, and it is going to increase till neutral axis. Again it is started decreasing. So इसको अगर मैं प्लॉट करके आपको दिखाऊं तो ये बनता है मेरा कुछ इस तरीके से। ओके, थोड़ा सा कमी रह गई यहाँ पे। चलिए, okay, so this is the case. चलो बन गया, समझ गए होंगे आप। दिस इज 0, दिस इज 0, दिस इज टाउ मैक्स विच इज कमिंग आउट टू बी हाउ मच, कितना हो जाएगा डी स्क्वायर बाय 4, और डी स्क्वायर से डी क्यूब कैंसिल, नीचे बचा डी, तो 6v by 4 bd और 3 by 2 of v over bd, and v over bd is also known as average shear, total shear force upon total area is average shear stress. So this you can also write it like v over bd, 1.5 times of tau average. Tau average, if you want to plot, it is v over bd. It may come like this. Okay, so there are 2 points where average is going to make this local variation, and this is parabolic in nature. This is parabolic in nature, and this is average shear stress. Tau average. Okay, so this is the case here. This is the case. Similar pattern can be observed for different section, maybe for circular section also as well, but वहाँ पे जो relation है वो change हो जाएगा। वहाँ पे 1.5 टाइम नहीं होता, circular case में मैं आपको लिखवाऊंगा, it is going to be 4 by 3, 1.33. Triangle के लिए भी you are going to get it at center line only, although in triangle the neutral axis is not at center, but the maximum shear stress in triangular portion also occurs at the center, and again you can say that variation there is as well parabolic. Okay, so this is a way to calculate shear stress distribution. Okay, the basic nature of shear stress in all the segments due to shear force is parabolic in nature. It is due to the parabolic in nature. Are you getting the point or not? So based on these results, you can deduce the similar expression in I section, in T section and all. So suppose if this is the case of I section, let me draw it for I section, how the shear stress varies. Yes, no, in I section, yeah, that is true for circular section. This is the neutral axis. So how it is going to vary? Anybody? so it is increasing. देखो एक चीज समझना है, यहाँ पे सारे पैटर्न खुद आइडेंटिफाई कर लोगे. इन shear stress distribution, this V A y bar over I into B. So this B, keep it in mind. From here to here, from just top of this line and just bottom of this line, area into y bar is constant, V is constant, I is also constant because I is of a whole cross section. The one thing which is suddenly changing from just top of this flange to the just top of this web is the width. Width is suddenly decreasing. Width is suddenly decreasing. So if numerator is suddenly decreasing, then fraction is suddenly increasing. So basic nature here is parabolic. Basic nature here is parabolic. But the moment you are jumping from flange to web, so due to the instantaneous decrement in the length, width, what is happening? This will be rapidly increasing, and again it is going to follow in the parabolic fashion. After neutral axis it will be decreasing in the parabolic fashion, and from this point to this point again there is sudden increment in the width. If there is sudden increment in the width, what is happening? If sudden increment in the width, then what is happening? Sudden drop. This is your sudden drop here. This is your sudden drop. After that, it will again parabolic. So here, this is also parabolic. This is also parabolic. And I also gave you the reason of this sudden jump. If width decreases, shear stress suddenly increases. If width suddenly increases, then shear stress again suddenly decreases. Okay, so one thing you can look at here, that from bending point of view, those sections are good where the more mass is located away from the neutral axis, like I section, T section. But for shear point of view, as you can see, most of the shear stresses are generating near to the shear neutral axis. So those sections would be preferred where more area is accumulated surrounding to the neutral axis. If as you are going away from the neutral axis, the shear stress intensity is already decreasing. So the nature of section for bending and shear are opposite. Bending needs more area at more distance from neutral axis. Shear means more area you will be needing and near to the neutral axis. So this is a prime difference between the shear stress and bending stress. Yes, yeah. And you know one more thing, that this tau, if you are seeing this A y bar over I, then this thing is having a uniform pattern. So multiply this B here. So this tau into B, shear stress into width, is known as shear flow. This quantity is known as shear flow. This is known as the shear flow. क्लियर है कि नहीं है? इसको आप क्या बोलोगे? शेयर फ्लो बोलोगे. ठीक है. So VA y bar upon I is the shear flow, or tau into B is also known as the shear flow. If I want to draw VA y bar upon I or tau into B, if I simply want to draw the shear flow diagram for this I section, then that I section diagram is coming out to be uniform, my dear friends. But when this is shear flow, but this is a shear stress. So in shear stress, due to the rapidly change of width, the functions are changing instantaneously. Okay, so this is the basic nature. Is it clear or not? अच्छा, अब अगर मैं ट्रायंगुलर की बात करूं, ट्रायंगुलर सेक्शन की बात, अच्छा टी सेक्शन का भी कॉमन सेंस से बना सकते हो. अगर मैं आपसे बोलूं कि यार टी सेक्शन का मुझको शेयर स्ट्रेस डायग्राम बना के दिखाओ, 4 ऑप्शन आपके सामने है, कोई एक चुनना है, तो आप देख लोगे सर कैसे चुनना है. ठीक है, आप देख लोगे कैसे चुनना है. क्या करोगे आप? If this is your T section, then somewhere here would be the neutral axis. Okay, so if somewhere here would be the neutral axis, so variation diagram is going to be like this. it will be increasing, sudden decrement in the width. Okay, this is the pattern for T section. Okay, चलो, अरे इसकी बातों को वो मत लो, सीरियसली मत लो। ये दूध वाला ये ऋषिकेश है, इसका काम यही है टाइम पास करना। चलो कोई बात नहीं। And he is also my offline student, ऋषिकेश। अच्छा, ट्राइंगल के लिए बता सकते हो व्हाट इज द shear stress distribution for triangular section? Suppose if this is B, suppose if this is H, how you can find the shear stress distribution? How you can find the shear stress distribution? न्यूट्रल एक्सिस होगा यहाँ पे टॉप से h/3 पे, टॉप से h/3 पे होगा न्यूट्रल एक्सिस। थोड़ा और ऊपर कर देते हैं इसको, थोड़ा सा ऊपर कर देते हैं, 1/3 2/3 लगना चाहिए। तो कैसे बनाओगे इसको? अच्छा, दिस इज न्यूट्रल एक्सिस or you can say centroidal axis, and this is your mid axis, h/2 axis. This is your mid axis. Why I am giving emphasis to mid axis? So here the height is till mid height. This is h/2. And this is h/3. This is h/3. ठीक है, this is h/2, this is h/3. So if you are going to draw the कुछ ना यहाँ पे सर्कल प्लस रेक्टेंगल का हाइब्रिड फॉर्म निकल के आता है, कुछ यहाँ पे सर्कल और रेक्टेंगल का हाइब्रिड फॉर्म निकल के आता है। तो shear stress डिस्ट्रीब्यूशन ऐसा होगा आपका। सो न्यूट्रल एक्सिस पे इस बार वैल्यू मैक्सिमम नहीं आती, यहाँ पे दी वैल्यू इज नॉट मैक्सिमम एट द न्यूट्रल एक्सिस। एट न्यूट्रल एक्सिस दिस टाउ इज 4/3 ऑफ टाउ एवरेज। ओके, बट इन दिस केस द टाउ मैक्सिमम इज एट द मिड हाइट एक्सिस and it is 3/2 of tau average. It is 3/2 of a tau average. तो ट्राइंगल के केस में आप ये याद रखना। क्लियर है कि नहीं है? ओके, इट इज नॉट मैक्सिमम एट द न्यूट्रल एक्सिस, इट इज मैक्सिमम एट द मिड हाइट एक्सिस विच इज 1.5, वेयर एज एट न्यूट्रल एक्सिस इट इज 1.33, है ना। एग्जैक्ट डेरिवेशन एंड एक्सप्रेशन नहीं लिख रहा हूँ, बस अभी पैटर्न पे ही हम ध्यान दे सकते हैं, वरना तो एक एक का डायग्राम इक्वेशन बनाने में पूरी क्लास निकल जाएगी। ठीक है, आर यू गेटिंग द पॉइंट और नॉट? अच्छा, ऐसा जरूरी नहीं है कि हर बार यू आर गोइंग टू गेट मैक्सिमम एट न्यूट्रल एक्सिस ओनली। दिस इज वन ऑफ द एग्जांपल। ओके, सो कभी कोई आपसे पूछे कि क्या मैक्सिमम हमेशा न्यूट्रल एक्सिस पे ही होगा, देन यू कैन से नो, इट्स नॉट पॉसिबल ऑलवेज, एज यू कैन सी द एग्जांपल ऑफ ट्राइंगल। ठीक है, अगर ये सिमेट्रिकल ट्राइंगल होता तो आपको एक बार को मिड हाइट पे मैक्सिमम मिल जाता, नहीं तब भी आपको मिड हाइट पे मैक्सिमम नहीं मिलता। चलो इसको भी देख ही लेते हैं। Suppose if we do have a section like this, suppose if we have a diamond section like this, yes, ऑब्जेक्टिव भी हो सकता है, इंटरव्यू में खासकर ऐसे क्वेश्चन ज्यादा पूछे जाते हैं। So this is my neutral axis as well as my mid height axis. This is my neutral axis as well as my mid height axis. So here as well you can see that maximum is not happening at neutral axis. Maximum is not happening at neutral axis. You know why? Because here the width is increasing. So if width increasing, then shear stress has to be decreased. So it may be, its diagram will look like this. B टाइप बनता है B, ठीक है, तीर कमान, ठीक है. So this is the maximum value. This is the maximum value. This is the maximum value, symmetrical. Or if this is the height, let's suppose this is height h, this is also h. Total height here is h 2h. Okay, total height is 2h and total width at the center is b. So this is located at a distance h by 4. This is located at a distance h by 4 and h by 4. This is also h by 4. This is also h by 4. Okay, so this value, they are symmetrical figures, top of the neutral axis and bottom of the neutral axis. This is anybody? 9 by 8 of average. It is 9 by 8 of average. This is 9 by 8 of average. So diamond section is a case where neither the maxima is occurring at neutral axis nor at center height axis, because both are matching here, and here the maxima is deviated h by 4 distance from the neutral axis. Okay, so that is the case. So this is the shear stress distribution in your diamond section. और सर्कल का भी बना के दिखाऊं क्या? सर्कल का तो क्लियर ही होगा. सर्कल इज ऑल्सो पैराबोलिक. सर्कल इज ऑल्सो पैराबोलिक डियर. Let's suppose the radius of this circle is r, and if you want to draw the shear stress distribution, then it is again coming out to be like this. This is tau max. It is 4 by 3 of tau average. Are you getting the point or not? Tell me everybody. Okay, ठीक है. अच्छा, जैसा टी बीम का आपका डायग्राम बना था, क्या सेम पैटर्न डायग्राम आपको एल बीम का भी मिलेगा? सेम पैटर्न डायग्राम you can also obtained for your L beam. भाई मतलब तो विड्थ सही है. विड्थ यहाँ पे सडनली क्या हुई? ड्रॉप हुई, और विड्थ ड्रॉप होने के कारण स्ट्रेसेस सडनली क्या हुए? इंक्रीज हुए. सो दिस पैटर्न इज ऑल्सो रिजेंबलिंग टू योर L beam. ओके, अच्छा, H सेक्शन का कैसा बनेगा? एनीबडी? व्हाट इज द shear stress distribution of H section? अगर मैं यहाँ पे H सेक्शन आपको बना के दिखाऊं, सो इट शुड बी लाइक दिस. Okay, so it is your neutral axis. So here the distribution is like, आप देख सकते हो सेंटर हाइट पे क्या हो रहा है? सेंटर हाइट पे क्या हो रहा है? यहाँ पे नेट विड्थ कम है, सेंटर हाइट पे एकदम से नेट विड्थ बढ़ गई, तो शुरू में जो आपका डायग्राम बनेगा दैट वुड बी like this, but suddenly when there is the increment in the depth, then drop would be there, and for incremented length this is the ओके, तो एकदम सिमेट्रिकल बनेगा। एंड ऑल्सो इट इज सेम फॉर योर प्लस सेक्शन। आइडिया ये है कि विड्थ एकदम से बढ़ेगी तो सडनली ड्रॉप आएगा। दिस इज क्वाइट सिमेट्रिकल, थोड़ा सा सिमेट्रिकल लग नहीं रहा है, इट इज वेरी मच सिमेट्रिकल। For plus section as well, the results are ditto same. Ditto means if you are keeping the dimensions in proportion. Okay, so all these are the important shapes of shear stress distribution. So it doesn't matter whether you are working in terms of H section, plus section, circular section. Okay, so they are going to happen like this. So this is about your shear stress distribution. Okay, so let me revise you one more time. So this is the basic equation to analyze your shear stress, V upon IV into AY bar. So although I have shown you a very simple case of rectangle case, that how the value of AY bar can be calculated, what is B, okay, although here B was kept constant, but in case of circle and triangle this B will be varying, okay, and V is the shear force, I into B is the moment of inertia and B is the width of the section. So मैंने टर्मिनोलॉजी लिख दी यहाँ पे और एक को रेक्टेंगल के लिए बना के दिखा दिया, एंड अकॉर्डिंगली विद कंसेप्चुअली विद द हेल्प ऑफ shear flow diagram we also calculated it for other numbers. Okay, so any doubt to anyone, tell me guys. तो यही रखते हैं सेशन में। अगले सेशन में मैं स्टार्ट करूंगा आपका कंबाइंड स्ट्रेसेस, और अगर मैं सिलेबस वाले पेज पे देखूं कि मैं कहाँ हूँ, सो वेयर आई एम इन सिलेबस पेज। सो जनरली अब मैं अपना रिवाइज देखूं तो कहाँ तक पहुँच गया हूँ मैं। आई हैव कंप्लीटेड दिस है ना। तो इन तीनों की, तो इन चारों तो टेंशन मत लीजिएगा, ये चारों आपके 1 घंटे के गेम है। तो अगला सेशन हम 3 घंटे का रखेंगे, 3 से 3.5 घंटे का। 1 घंटे में अगर हमारी ये 4 चीजें भी कवर हो गई, स्टिल वी विल बी एबल टू कंप्लीट कॉलम एंड डिफ्लेक्शन ऑफ बीम इन ए गुड मैनर। ओके, इज इट क्लियर? सो दिस इज द टास्क फॉर लास्ट सेशन, और जब तक खत्म नहीं होगा हम वो सेशन छोड़ेंगे नहीं। सो बट यस, वन रिक्वेस्ट इज देयर, इंस्टीड ऑफ 2 आई विल स्टार्ट दैट सेशन एट 2:15। ठीक है, 2 की बजाय वो मैं सेशन 2:15 पे चालू करूंगा, एंड लिंक वुड बी डिफरेंट फॉर दैट सेशन। आई होप यू ऑल नो दैट। ओके, ठीक है, सो लेट्स कीप द सेशन ओनली अप टू हियर, और इसी के साथ अपना तीसरा सेशन, तीसरा पोर्शन भी खत्म हुआ। एंड यस, सो लाइव मेंटरिंग प्रोडक्ट इज देयर विद ऑल द न्यू आइकॉनिक सब्सक्रिप्शन डियर, और स्पेशल क्लास आज 10 बजे मिलेंगी। इसमें 20 क्वेश्चंस की एक सीरीज होंगी, 20 क्वेश्चंस, इंपॉर्टेंट क्वेश्चन फॉर यू गाइस, एंड यू गाइस कैन चेक आउट द ब्रांड न्यू अपडेट्स ऑन अनअकैडमी आस्क इट आउट, एंड दिस इज आवर ऑफिशियल टेलीग्राम चैनल। और बहुत सारा कंटेंट अवेलेबल है हमारा स्पेशल क्लास पे और यूट्यूब चैनल पे, बट स्टिल वी रिकमेंड आवर लर्नर्स टू गो फॉर आवर प्लस एंड आइकॉनिक प्लान। द रीजन इज बिकॉज आपको यहाँ पे ये मिलते हैं सारे बेनिफिट्स, डेली लाइव क्लासेस, वीकली टेस्ट, स्ट्रक्चर्ड कोर्स, क्रैश कोर्सेज आर आई वी, एंड अनलिमिटेड एक्सेस टू द कंटेंट, है ना। आइकॉनिक में आपको कुछ बेनिफिट्स एक्स्ट्रा मिल रहे हैं, जैसे डेडिकेटेड डाउट क्लियरिंग एजुकेटर आपको दिया जाता है, स्पेशलाइज्ड नोट्स, पर्सनलाइज्ड सेशन एनालिसिस, स्टडी बूस्टर सेशन, स्टडी प्लानर एंड पर्सनल कोच, दे आर आल्सो गिविंग यू। सब्सक्रिप्शन की कॉस्ट ये है, आप AISH1 लगा के सब्सक्रिप्शन ले सकते हो डियर, बट इंस्टीड ऑफ 10% इफ यू वांट टू अवेल 20% डिस्काउंट, तो आपको अपना सब्सक्रिप्शन कल रात तक प्लान करना होगा। सो नॉर्मली यू विल बी गेटिंग 10% ऑफ, बट टिल टुमारो नाइट इफ यू आर प्लानिंग एनी सब्सक्रिप्शन यू विल बी गेटिंग इट बाय एट 20% ऑफ। सो थैंक्स अ लॉट, टेक केयर, और 2:15 पे स्टार्ट करूंगा, डोंट फॉरगेट, आई विल स्टार्ट द क्लास 2:15 एट 2:15। लकी भाई, ये जो कोड आपका वैलिड है ये कल रात तक अगर आप लगाते हो तो 20%, उसके बाद लगाते हो तो 10%। ओके, चलिए डियर, सो बाय बाय, 2:15 पे मिलते हैं फिर से। टेक केयर।